Okay, now I'm on it. Right, so in this last lecture, I will try to outline the proof of the structure theorem. I will relate it to the Gleason-Yamabe theorem that we talked about last time. And I'll try to give some application, some further application. So remember the structure theorem has weak forms, and I'm going to state a strong form. So first, state the weak form. So it can be stated like that. You given K, so it will be K, with this C of K. That if A is a finite subset of the root P, such that A times A is less than K times A, then A is contained inside XH, where H has sign minus C of K, and H is virtually nilpotent. Okay, so this is the form. And in order to state the strong form, I will first define the notion of a progression in a general group progression. So, progressions. So remember that arithmetic progression is just something like A plus B. So people in additive combinatorics also consider what's called a generalized arithmetic progression. Arithmetic progression for T and P. And this is plus B is Beaton group. And you take B the box in ZD. The ni's are integers. And you let pi be a homomorphism from ZD to D. Then you define A to be pi of B. It's called a generalized arithmetic progression. Okay. So this is a centered, sometimes people say centered generalized arithmetic progression because it's centered around 0. You could also translate it and also call it generalized progression, but for me, I would take just this definition. Okay. So, for example, in Z, it looks a bit like this. So this is Z, and maybe you have 0 here, and then -1, 1. And then you have here so you have some other number A, and then you stick like this, and then you keep going, and then you go up to AN2, and then it's like this. It looks a bit like this on this with the image of the box. If you have now an arbitrary group, G, then you need to pick some elements Q1, GD, and G. And you pick also some integers N1 and D, and you let P of Q1 is V, N1 and D be, by definition, the set of group elements such that G can be written as a word in the generators of GIs. And their inverses in such a way that, the number of occurrences of each GI and its inverse is at most Ni. Okay, so that's the definition. And I call this group, the group progression generated by the PI with segments right. So D will be called the rank. So, for example, if all the NIs are the same, and if D is the group generated by S, and S is exactly those generators, these generators, then you see that this progression is closely related to the ball of the K graph of your group. So the P is say contains the ball for this D N, and it contains the ball for this N. This is the N ball in the K graph. Okay. Okay. So, for example, if you take so, for example, another example, if you take P to be the Heisenberg group, so nilpotent group X, Y, Z are integers. Okay, so that's a step 2 nilpotent group, and you can take G1 to be 1, 1, 1, 1, 0, 0, G2 to be 1, 1, 1, 0, 0, 1. then it's fairly easy to see that the P to be P of G1, G2, N1, N2. So this, if you do all words in these guys with at most N1 of G1, at most N2 of G2, you see in the abelian parts you get just X and Y of size at most N1 for X and N2 for Y, but in the Z parts you get all products for X and Y. So they go up to product N1 and 2. So this will be contained, and it will also contain the set of N1 X by Z, where X is less than N1, Y is less than N2, and Z is less than some constant, some explicit constant, maybe 2 or 4 times N1 and 2, and it will similarly contain a set of 1, 1, 1, X, Y, Z, where X is less than 1, Y is less than 2, and Z is less than maybe some other smaller constant, N1 and 2. Okay? Small computation should include that. Yeah, I should have said here that in the case when G is an abelian group, then you recover exactly the generalized arithmetic progression I was talking about. It's just the image of the box, right? Because if you look at in ZD, the number of elements in the elements in ZD, which can be written like that, the GIs are just the canonical generators of ZD, is precisely the box. It's side X minus Ni and Ni. So for the non-open group, there is something similar. So you see here in particular that in this example, the size of P is roughly N1, N2 squared. Right? Because you have N1 possible value of X, N2 of Y, and N1 of 2 of Z. Okay. And so that's first. You also see that if you take P times P, what do? You just increase maybe by a factor 2 the size here. So P times P will be also of a similar size as P. So P has small doubling. The doubling does not depend on N1 and N2. The ratio here does not depend on N1 and N2. So this is an example of an approximate group, or at least a set of small doubling, which is not a finite group. It's not close to a finite group. So there's no finite subgroup of this group. And it's also not an abelian, it's not a progression, not an abelian progression. So it looks more like a ball in this K-graph. Except it's a bit of a distorted ball. If N1 can be allowed to be much bigger than N2 can be much bigger than N1. Exactly. Okay, so
So what's the H in this situation?
It's the ambient group, which is
okay.
Okay, so now that's a general progression. So a nil progression of step S is a nil progression P such that the group connected by G1 QB is S set nilprogressions. So that's the definition. Yes. And so this is in fact equivalent to say that all commutators commutator of this kind, of all commutators of length at least s in the GIs vanishes. So it's well known that if you have a generating set, all of whose commutators of length d vanish, then it generates a nilpotent group. Okay, and so if you're in this situation, then this is the first proposition is that any nil progression is an approximate group. So if so. With this some k, which is k of d and s only, and another constant c, which also depends only on the s, such that any s step progression rank b with the side length. So the side length needs to be not too small. I'm not going to prove it here on the board, but this example is actually what's going on. The proof involves a bit of commutator calculus, but it's okay.
So it's not true, the side length is small?
No, it's been told, it's not all. It's the length is too small, so yeah, you may need to take a few more powers of p so that it stabilizes. Maybe some stupid code. Okay. So then with this in hand, I can state the strong form of the theorem. So now the strong form. The strength form says the same thing, but it gives some more information on H. So furthermore, we have an exact sequence of that. Where n is finite, L is non-constant, so we have this, and there's this P. Now, linear progression. Such that I inverse P containing A minus 3 and 2. And A not only is contained inside XH, but it's contained inside X. And those X again found the size. So this means that your set can be covered by boundedly many translates of a nice set which we call these sets coset nil progressions because they are pullback of a nil progression by homomorphism with finite kernel. And moreover, this nil progression is contained in A minus 2, A2. So it's really inside a small part of it. And on top of this, the rank and the set of C all depend are bounded in terms of K only. So, okay, so the theorem can be summarized by saying that and every approximate group is controlled by a coset nil progression. So they are basically only every approximate group is essentially every finite approximate group is basically just an extension of a finite group by some nil progression. There's another example. So this is for finite approximate groups. So you could envision a structure theorem for, instead of taking finite subsets in discrete groups, you could look at bounded subsets of locally compact groups. And again, with the same definition, A times A contains X times A. X is finite. So approximate groups, but not finite approximate groups. And then you would realize that there is another class of examples that don't fall into the class of either finite groups and progression and extensions. There is simply the neighborhoods of the identity of a V group. For example, take a compact group like S of VR, take a small ball around the identity. Then it's an approximate group. The ball of radius 2R can be covered by a bounded number of balls of radius R. Okay, it's an approximate group, but it has nothing, it's not close to a group or to a
trivial group.
Yeah, so it's close to the trivial group, exactly, but in some sense. So you can try to find a structure theorem of that kind. And there's a student of Tao who did that. So there is a structure theorem now available for arbitrary approximate groups that are bounded subsets of a locally compact group. And so it has a bit of a similar flavor, but you need to take into account these neighborhoods of the identity. So basically you need to be able to say, so the point is that the dimension has to be bounded. If you have an approximate group like that in a D group, then the dimension of the D group must be bounded, because in order to cover a ball of twice the radius by K translates of a ball of radius R, you need a bound on the dimension. Okay, so anyway, so that's in the science. So I'm going to give an outline of the proof of the theorem. So 2 weeks ago we already did a big chunk of the proof. Because we showed this velocity model theorem. And so the proof started by taking an outer product. Okay, so if we take an arbitrary outer product of an arbitrary sequence of groups, and we took a outer product of an arbitrary sequence of k approximate subgroups, finite k approximate subgroup. So let me remind you that this means, this means an is contained inside can be covered by at most k translates to an, and we also have the assumptions that an is symmetric and contains the identity. Okay. And we made the observation that A inherits those properties. If you take the outer product, then you get the same thing. So A will be a k approximate group, except it's not going to be finite anymore, unless there is an upper bound on the size of the ANs. That's not the case we're interested in. So, and that's because if the xn's all have at most k elements, so an product of bounded sets of cardinality at most k has also cardinality at most k. So, okay, and we call it a pseudo-finite approximate group. Because it's an outer product of finite approximate groups. And we had Khrushchev's model theorem, which, let me remind you, was telling us that there exists G, a locally compact group, and there exists I from something generated by this pseudo-finite approximate group, and the subjective homomorphism with the property that that pi of a squared is a compact neighborhood of the identity. And with the second property that for every two subsets, F here is compact and E is open, you can find an integer k naught, and you can find a subset of that form. contained in A such that F the image of F contained B contained U. So, in other words, you can approximate the topology here by a product of finite subsets of A or small part of A. So in particular, this map is essentially almost injective. The kernel of this homomorphism is contained in a small part of A. You could take F to be a density here, for example. So you have a model of your pseudo-finite approximate. Okay, so let me open a parenthesis and answer a question Cornelia asked 2 weeks ago. So Cornelia asked, can G be a compact EU in this theorem? So yes, it can be a compact group. It can be, for example, R mod C. For example, we could take AN or G mod NG. And remember how the topology was built. The topology was built out of subsets SKN inside AN. And so if you subsets such that if you take a power is such that S to the power K is still contained in AN or maybe N to the 4. And so here, for example, you could take everything between minus N of K and N of K, a small interval, and then you see that the pi that you built this way. So here I took the full group, so A is a group, but the limiting group is just R by C. So you certainly can have compact groups. However, if G is compact, G must be a B. Let me tell you why this is true. So if G is compact, then because of the first point here, pi of A squared is a neighborhood of the identity, and because it is surjective, the bounded power of A squared will map onto G. It's a compact neighborhood of the identity, so if you coset, you keep multiplying. We're going to cover all of G. Okay, so that theorem with some K naught, such that pi of A K naught is all of G. But this means that A of K naught is a group. So, in particular, you get that AN in the group almost every N, almost everyone. And then the question becomes: suppose you have a product of finite groups, or an ultra product of finite groups, pseudo-finite. Can it map onto? Can you have a homomorphism, abstract homomorphism, from a product of finite group onto a compact, simple Lie group? So Lee, if it's Lee, that's okay. But as a fact, no several compact E group can be a homomorphic image of the product of finite groups. And so this is a non-trivial fact. And it's actually this was a question of Zilber, for quite a long time, and he recently realized how to prove it and how to actually see that it follows from a deep result of Nikolov and Siegel. And actually, a few weeks, a month ago, there was a paper independently, a paper of Nikolov, Schneider, and John, showing just this, okay, showing that this can happen, among other things, but I'll tell you the proof. The proof is based on the deep work of Nikolov and Siegel. So one of the things that Nikolov and Siegel show in their work on words and word mass. So Nikolov and Siegel, they show that there is, so given an integer d, there is an integer e, so that for every finite group d, generated, and for every degenerated, say, group G, and say G1, blah blah blah, GD, a generating set. The entire commutator group, so every commutator, or every product of commutators, can be written as a product of boundedly many commutators. So they show something like this. To some power. Some power means, a product of words of this type. So in particular, if you now have an arbitrary finite group, and you see that in particular, for every word in the commutator of the free group, and for every G finite group, and for every GH two elements in G, you see that a word in G and H can always, a word that belongs to the commutator of the free group can always be written as a word that belongs to something like that. E. Okay. That's a very strong fact about finite groups, arbitrary finite groups. And now you see that if this holds for every finite group, then taking an ultra product of finite groups, it will also be true. If I replace G by a pseudo-finite group. And if I take any quotient of a pseudo-finite group, then it will again be true, quotient. However, there is no chance that such a thing could be true in a simple, compact, simple Lie group, And the reason is, in a compact simple Lie group, you have neighborhoods of the identity which are invariant under conjugation. So conjugation, because it's compact, you stay near the identity. So if G and H are near the identity, then this entire commutator is near the identity. So the whole thing is near the identity. And because E is bounded, the whole thing is actually in a small neighborhood of the identity. Okay, but however, if you take a long enough word, then it can go anywhere. Okay, so it can't be a compact Lie group. A compact, simple. Or if it's compact, it must be Lie. Okay, so the difficulty is not when G is compact. Okay, so the difficulty, so remember we have this Minkowski model theorem, or model theorem. If G is bounded, if G is the identity, then we saw, or if G is compact, then we saw that it's enough to conclude the theorem that all the ANs are controlled by a finite group. The difficulty really lies when G is not compact. G is not compact, and even when G has no compact open subgroup. Because if you have a compact open subgroup, then you can always pass to the open subgroup, pull back the open subgroup to here, and because the image of A is the compact neighborhood of the identity in G, its intersection with the open subgroup will be enough to cover the whole of A in bounded domain process. So you can always assume it can always pass to an open subgroup of G. So in particular, in the case of when G is totally disconnected, and we saw at the end of the day that that's enough to conclude that the ANs are controlled by a finite group. So the problem lies when G is not totally disconnected, so there is some connected component. It's not compact, and so that's exactly the same problem which is faced when you're trying to prove this Gleason-Yamabe theorem, this classification of local compact groups. So if you apply, you can apply the Gleason-Yamabe theorem to G, and conclude that to passing to an open subgroup we can assume that C is approximated by Lie groups so this means that for every neighborhood of the identity you can find a normal subgroup of G which is contained in U, so it's compact, closed, such that G mod K is D. So in particular, so this means that we may assume that G is a Lie group just by taking K inside pi of K squared. mod out, right? Then the same properties will be kept. So we have this map, and remember it satisfies these two assumptions that pi of a squared is a compact neighborhood, and that given any compact containing some open set, if I pull this back to characterized by the pseudo-finite approximate group A, I can approximate it, I can find inside it, in between it, a pseudo-finite set. So this is almost injectivity. Okay, so that's where I'm now. And so now the proof the proof is essentially modeled on the proof of the Gleason-Yamabe theorem. So remember, the Gleason-Yamabe theorem had two parts. It was you wanted to show that, so you want to show that every locally compact group has an open subgroup which is approximating the Lie groups. First, you show that it has an open subgroup which is approximated by NSS groups with no subgroups. That's the Yamabe part. And then you show that NSS groups must be Lie groups. That's the Gleason part. Okay. And so here we are going to do something similar. We're going to prove two propositions. Proposition 1. That's the reduction to NSS. We're going to show that if A is a pseudo-finite A plus B, then there exists H in A to the 4 such that H is a subgroup which is so in fact it's not necessarily normal in A, but it's normal in a large part of A. So the H is normal in B, where normalize H. B is B is a positive proportion of A. So in this business, there is always we always apply this Sanders-Coty-Sars lemma, which was used to build topology from in the Kuchowski-Lie model theorem. So we can always pass to a much smaller approximate group, which has the property that its powers up to a certain point still belongs to A to the 4. Okay, so we can do that, and then what I claim is that this subgroup is normalized by one of these Sanders neighborhoods. And B mod H is NSS, which means that i.e. it has no it contains no subgroup. Yeah. So you sort of isolated some normal subgroup inside, modulo which you don't have small subgroups. And proposition 2 is that if A, again, is a pseudo-finite approximate group, which is NSS, then it's basically a nilprogression. So then there's this P in A4, which is a nilprogression, or pseudo-nilprogression. It's another product of nilprogressions of given step and given rank. And it's a positive proportion of A. So, so A is, so you can write it either like A over P is finite, or if you want, you can write it as A is contained inside few cosets. It's controlled by P. And so these two propositions imply the theorem. Essentially a reformulation. Okay. So again, the proof will be fairly close to the proof of the Gleason-Barré theorem. So proof is a copycat. So you introduce this, so if A is a k-approximate group, again you introduce this notion, this quantity, which is the supremum of all integers n, such that the entire geometric progression belongs to A, and we define the escape norm of V with respect to A to be the inverse of this. And you prove a lemma, which is similar to the Gleason-Barré lemma. Which says that given you can find V inside A to the 4, which will be a C of K approximate group. And we'll have the property that when we give an H and V, you have these three properties that I stated last time. The escape norm of the product is at most constant. Is the escape norm B. That's the escape norm of pH. And finally, the same thing with the commutator. So the proof of this lemma is the same, essentially the same as the proof of the Gießen-Yamabe lemma. So the idea was to build a bump function and take a convolution product of this bump function, and approximate the escape norm by the infinity norm of this formal derivative. The same thing works. You don't have a harm measure to take convolution, but what you do is you replace it with the counting measure of A. You take this is the average that you take to smooth things out. And okay. So the proof is essentially the same. Essentially the same. So then a consequence of this lemma is that now you can see where the normal subgroup comes in. So let H be the set of elements B with escape norm equals to 0. So that's precisely the set of elements in B. So the entire cyclic subgroup generated by H lies in B. Lies inside B. So it's a set. A priori, it's not clear it's stable under multiplication. But because of item 2, this is going to be stable under multiplication. Both of them are 0, this tells you product also is 0. So this was the same sort of difficult point that Sarah was pointing out in his Bourbaki seminar, just on the eve of the solution to the fifth problem in the 50s. So it's the same problem. So this becomes stable, and this becomes 8 by 2. H is a subgroup, and by 1, H is normalized by B. Okay. So I haven't told you what number 3 is for. It's going to be quite clear. So first of all, just from these 2 points, you get that you get a proof of the first proposition, reduction to emphasis. Because anything that's outside H will have positive escape norm, which means that at some point its powers will leave B. Okay. So if I look at B mod H, going to be an approximate group in the quotient. And this approximate group will be MSS, will not contain any subgroup, because by definition, if the cyclic group generated by some element is in B, it has to be in H. So this means that B mod H will be I will have no small subgroups. Okay, and so that gives a proof of proposition 1. And now to go from NSS approximate groups to nil progressions, this is where item 3 will come in. And you need to see where the nilpotency comes from. So, and this is going to help you. And also the fact that B is finite. So the fact that B is finite implies that there exists an element in B with the smallest positive escape norm. So this means that there exists some U with the escape norm U positive and minimal. But then you see that U is centralized by D. Right? Because if I take the commutator of U with any other element from D, as long as the norm of H is smaller than 1 over C, and so here what I need to do is maybe change V into V prime, set of elements in V with escape norm is less than 1 over C. And this will be also a big part of B, because you see that if you look at the Lie model, it's precisely the pre-image of a small neighborhood of the identity, slightly smaller than pi of B. So, and anything in here will give you, when I take the commutator, will give you strictly an element of escape norm which is strictly smaller than the escape norm of H, of U. And because of the minimality, it means must commute. And so then yeah, so then you see that if you look at U, so for if you are on the side, you do this for each B, for each n, and so you get some UN, the smallest escape norm. Then you can look at all powers of n and up to maybe NB of UN, and you look at this, and you call this U sub t. And you see this way that pi of U sub t is a non-trivial one-dimensional subgroup. Of U commutes with everything in B prime. The image of B prime by B by pi is a neighborhood of G, neighborhood of this D group G, and everything commutes with it. So in fact, this one parameter subgroup will be, it will be central. And so you found one parameter subgroup which is central. Okay, and then from this point on, you apply an induction. So the idea is then to induct on the dimension of G by modding out by the group generated by this one parameter using. And so remember that I recall, but what we need to prove is we need to prove that there is a nil progression which controls A. And so we're going to get this way that G will be nilpotent, but we need a nil progression. So so the idea is you quotient by this UN, and you quotient each Vn by this UN. You get a new approximate group, a new Lie model, but the limiting group will have dimension 1 less. So, and there you can find a nil progression by induction, and you need to pull it back to Vn. It requires a bit of work, but it can be done. In fact, when you look at the details, you will see that in order to make this rigorous, in the paper we had to go outside of the category of groups, or local compact groups, and talk about the local. The issue is slightly delicate. The issue is that we can't just mod out by the full group generated by UN. We can't mod out by the full group generated by UN, because when we do this, it may, in quotient, the quotient may not remain NSS. It may produce some further torsion in the quotient. It's easy to see some examples like that. This is a PZ for Z. So you can find here some two-dimensional generalized arithmetic progression. And you see that if you quotient by the entire group generated by the element of smallest escape node, then maybe it will kill the entire Z factor and you end up with some quotient which has some torsion. So you can still get a proof of the weak form of the theorem without having to go through local groups. But then you get only the weak form. But if you want the strong form where you have the nil progression and you have this kernel which is containing A to the 4, we had to go through local groups, and the idea is if you have a local group, you can quotient by local. So you want to quotient by not the full group generated by UN, but the powers of UN that up to this progression, this geometric progression, up to the time when it leaves B. Okay, so you need local groups for this. If you look at the exposition in the Bourbaki seminar by Van den Ries, he avoids local groups, but as a consequence, he does not get a strong form. Okay. All right. I could stop here, or I could give you an application to the theorem of Benjamin Tesla. Okay. It's up to you. Is it cute? Is it cute? It's quite cute. So. What did they what did they do? They were interested in the following class of vertex transitive groups. So you're given two integers, and you look at this class of groups, a class of graphs. Vertex transitive. Finite graph. With the property that the diameter is quite large, so the size of the, so let's say d regular, divided by the degree, there's a constant times the diameter of the graph to centrality. So that's the size, the number of vertices. So assume that the number of vertices is bounded by the diameter to somehow. Or in other words, the diameter is bigger than the small power of the number of vertices. So the diameter is quite big compared to the number of vertices. Okay, so for example, we could take a large cyclic graph. Diameter is like n over 2, so here d equals 1 in this case. Okay. And the theorem is the following. So if f, so Vn is a sequence in this family of graph, such that the diameter tends to infinity, then this sequence Gromov-Hausdorff converges, first of all. Sorry, there is a subsequence. Then there exists a subsequence. Which Gromov-Hausdorff converges, and we can identify the limit. So, okay, so actually we'll show CG with the norm, with the invariant norm. So the only limit metric spaces are just set to R with a Minkowski norm, with an arbitrary norm.
Assume that these graphs are vertex transitive.
Vertex transitive.
That means the isomorphism vertex transitive.
On the vertices. Yeah. D is the optimal. D is the optimal path. It could be suboptimal. Yeah.
Converge to the smaller torus.
Smaller. Okay, and you know, one feature of this is it's independent of the degree. There's no bound on the degree, so it doesn't matter as long as you have this. So you can't, for example, you cannot approach a sphere. So when Benjamin gave a talk on this, he actually showed us the soccer ball, which is a truncated icosahedron. So it's vertex transitive, and it looks like a ball. But this theorem tells you that you can't go much further than that.
This sounds like a polynomial growth theorem since there are groups there.
That's right.
These automorphism groups.
Yeah. So the proof,
Except that the stabilizers can be pretty large.
that's right. Yeah, that's it. So that's the proof. So the proof is just it is just a sequence of small observations which I mean the proof can follow from general principles from the structure theorem. So the point is you take G and here, you give the automorphism group of and you take Sn to be the set of elements in Gn which move some base points. Okay, some fixed points in the vertices. And at most 5, most 1. Okay, so this is going to be your generating set. And then this assumption will be translated into the diameter of the n is Sn. Yeah, it's bigger than the n over Sn to the 1 over d. Or you could say that the ball of weight is the diameter is which is equal to Gn divided by the ball of weight is 1 is at most equal to the diameter to the power d. So in this form it looks like a polynomial growth condition. Means also which is independent, which is not sensitive to the size of the generating set. So the ratio between the ball of this radius and radius 1 is at most the radius to fixed power. So it's and then we are in a group. We are in a finite group because everything is finite. And so you can argue, like in Gromov's, at the beginning of Gromov's proof of his theorem, that there will be some small power of Sn which will have power of doubling. So you can get that Sn to some power and P1 will be less than some constant to the Sn N1. So from this point you can apply the structure theorem, and if you apply the structure theorem for approximate groups of small doubling, if you apply the strong form of it, you see that the strong form, so a consequence of the strong form, is the following. That's given
given K. This sub N1, depending on K. If G is a finitely generated group, and if S to the N is less, S to the 2N is less than K times S to the N for some N bigger than 1, some, then S to the 2N is less than C to the K S to the N for all. That's a consequence of the structure theorem. So if you have some doubling at some stage, some large stage, then it will stay doubling at all subsequent scales. And the reason for this is that so S to the N is controlled by a coset nilprogression, something like P. And so if you take any power of this, it will be controlled by P to the K. But the point is that if P is a nilprogression, then P to the K is also a nilprogression with the same sets number generated. So it's also an approximate group with the same constant. Okay. So P to the K is a C of K approximate group for all P to the K. So it keeps it has the same doubling. And yeah, so you get this. So if you apply this to your situation, you see that for some N1 you have some doubling, and then at all subsequent squares you have the same doubling. So this means that the Gromov compactness criterion for this family is mathematically applied. Let me remind you of the Gromov compactness criterion. You have this Gromov compactness. If you have some family of compact metric spaces, then F is pre-compact in Gromov-Hausdorff topology if and only if you have this property that when the epsilon exists some n of epsilon such that every matrix space in the family can be covered by n of epsilon balls of radius epsilon. So that's exactly what this gives you. So, you get, so that's the hardest point in this theorem, is somehow to show that you have, in this situation, the hardest point is to show that you have convergence, that you have pre-compactness. That's what this gives you. And so you know that there exists a subsequence which converges. And then, okay, so then they have a way to, an interesting way to conclude that there is another way, which is just to say that you get, in this convergence, because it's vertex transitive, so in the cohomology of convergence, if you take a limit, this space X will be connected because it's graphs, so it will be locally connected, and there will be an action. It will also be homogeneous, so the isometric group of X will act transitively on X. So we are exactly in the situation of Montgomery zipping. We have a locally connected space, finite dimensional, where the isometric group acts transitively. So we can conclude that it's a Lie group. Okay. So we can apply this Montgomery zipping lemma, which, by the way, is in this case, because everything is compact, is just an implication of Peter Bach. You don't need to listen about it. To conclude that X is G mod H, where H is Lie group, is a compact Lie group. But it may be, it's, you know, so this does not rule out the sphere. So how do you rule it out? This homomorphism of convergence comes with, is equivariant, right? Because we have a group action here, group action with limit. So in this situation, this is called equivariant homomorphism of convergence. What you get is a sequence of epsilon representations of Dn in the isometric, in the limits. So there are epsilon representations in the sense of Cardan relativity. So this means that phi n of gh minus phi n of g n of h is uniformly small. And okay, but it's well known, it's a theorem of Cardan. Actually, in this context, it's a theorem of Turing. One of the early papers of Turing. That an epsilon representation of a finite group into a Lie group must be close to a representation. So it must be close to a genuine homomorphism. So you get a homomorphism from Gn, so it's close to a homomorphism from Gn to G, but because these maps are subjective, you get that G must be approximated by finite groups. And so this contradicts Jordan's theorem, unless G is big. So that's the proof. So yeah, so there's Benjamin Fiumke and Tessa, they argue a bit differently, using basically more of the structure theorems, using that you have really a nil progression, and then showing that this nil progression in the limit will give you an nilpotent group. Yeah. And they'll argue that nilpotent compact group must be. Yeah, so there is, we discovered
So the conclusion is
a number of people.
the billion or has a billion subgroup of a control details.
Yeah, so because it's a compact connected Lie group, it cannot be approximated by finite groups, unless it's a choice. G is a choice. And you get a G is a torus with some limiting geodesic metric, which is invariant. But every geodesic metric in the Lie group, which is invariant, has to be basically given by a no. And that's actually a very general theorem of Berestovsky. Take a connected Lie group, not even compact. If you have a geodesic metric, which is left invariant, it has to be given by some norm of the Lie algebra. And so it's like the Riemannian metric, but Carnot character. But here,
it's a beam. It's just okay.
It seems easier than everything we described before, because we're in a compact setting.
That's right.
The groups are compact. Thanks.
Thanks. So showing paper is it's a short paper. It was, I think, we discovered by Benjivax some years ago.
It was probably done in Cambridge, right?
It was done in Princeton. Or maybe in Cambridge, yeah, maybe. Or maybe in Princeton, but he thanks von Neumann, so maybe it's not only Princeton. But it's a special case of Kaldan's theorem about absolute representation. Kaldan is about actually minimal. Absolute representations of minimal.